Hello students, in these slides I will going to discuss about the lens makers formula. So while building the lens makers, which formula they are using, hence the name lens makers formula. Lens makers formula, to derive it, I will going to consider a convex lens, okay, which is made up of a absolute refractive index of a medium mu2 and placed in an optical radar medium n1. So this is medium 2 which is kept in a medium 1, where medium 2 is having a refractive index n2 and medium 1 is having a refractive index n1. So this is the point object kept along the principal axis. So to form the image, two rays we are considering, one in the direction towards optic center, another one is the above green light. Okay, so they are converging at a point on the medium once again. This is ABC is one interface, ADC is the other interface, where I is the image formed by the lens. So this is a diameter taken from A to C, which is known as aperture. So U is the object distance, V is the image distance. Let B and D be the poles and C1, C2 be the centers of curvature, where R1 and R2 be the radii of curvature of the two surfaces ABC and ADC. So step 1, refraction at ABC, first interface, like this, where n1 is the rarer medium refractive index and n2 is the denser medium refractive index, where n1 is also called as object medium refractive index, or it is a refractive index of object space. N2 is called as refractive index of image space. This is the object which is kept in a rarer medium, and this is the principal axis. To form the image, two rays we are considering, the image is formed in N2 medium. Okay, that is I1. So here this is C1, which is the center of the sphere of which the lens is a part, and the line drawn from the center of sphere or a center of curvature to the curvature point, any point, it will become the normal. So and these two are the angle of incidence and angle of refraction. So radius of curvature for this particular surface ABC is R1. So by the laws of refractions through the spherical surface, the final result we got, a refractive index of the image space divided by image distance minus a refractive index of object space by object distance is equal to difference in the refractive index of image space to the object space divided by radius of curvature. That formula we are using here to solve this. Refractive index of image space by image distance minus refractive index of object space by object distance is equal to Ri of image space minus Ri of object space divided by radius of curvature. So for the refraction through ABC, I1 is a real image and O is the real object. Equation 1, it will become N2 by BI1 minus N1 by OB is equal to N2 minus N1 divided by BC1. So this is equation 2. Step 2, that is refraction at ADC surface, where C2 is the center of curvature for this ADC spherical refracting surface, N2 is the denser medium refractive index through which the incident ray is coming, and N1 is the rarer medium refractive index in which the image is forming. So I1, which was the initial image formed by the first refracting surface, act as a virtual object for the second refracting surface for which the image is formed at I. See, R2 is the radius of curvature for this refracting surface. For refraction through ADC, as I told, I1 act as a virtual object and I is the real image. Equation 1 becomes N1 by di minus N2 by di1 is equal to minus of N1 minus N2 divided by dC2. So this can be written as N2 minus N1 divided by dC2. So for the thin lens, di1 is nearly equal to di1 and bi1, both are same. Equation 3 becomes n1 by di minus n2 by di1 is equal to n2 minus n1 divided by dc2. This is equation 4. By adding equation 2 and 4, n1 by ob plus n1 by di is equal to n2 minus n1 multiplied by 1 by bc1 plus 1 by dc2. This is equation 5. Suppose the object is at infinity, then OB value will become infinite and DI value will become focal length. So equation 5 will become N1 by F is equal to N2 minus N1 multiplied by 1 by BC1 plus 1 by DC2. This is equation 6. Here F is the focal length of the lens. By sign conventions, BC1 is equal to plus R1 and DC2 is equal to minus R2. Therefore, 1 by F is equal to N2 by N1 minus 1 multiplied by 1 by R1 minus 1 by R2. This is the lens maker's formula. Note, compare equation 5 and 6. N1 by OB plus N1 by DI is equal to N1 by F. But OB is equal to minus U and DI is equal to plus V. So N1 by minus U plus N1 by plus V is equal to N1 by F, or 1 by V minus 1 by U is equal to 1 by F. This is the final equation for the thin lens formula. Power of a lens. It is defined as the tangent of the angle by which the lens converges or diverges a beam of light falling at a unit distance from the optical center. The ray of a light is incidence parallel to the principal axis at a height of h from the optical center. The ray is bent by an angle delta and it is passing through the principal focus capital F. If small f is the focal length of the lens, OF will become F. From figure, tan delta can be written as h divided by F. If h is equal to 1, then tan delta is equal to 1 by F. For a small angles, delta is equal to 1 by F. Hence, power of a lens is P is equal to 1 by F, where 1 by focal length. So, reciprocal of focal length itself is power. Note, so power of a lens is the measure of the convergence or a divergence of a light falling on that lens. Second one, a lens of a shorter focal length having a more power bends the incident light more. Either it is a converging or diverging. Third one, the SI unit of a power of a lens is taken as a diopter, so which is represented with a letter capital D. 1 diopter is equal to 1 per meter because power of a lens is reciprocal of focal length. So 1 by 1 meter means it will become 1 per meter. 1 diopter we can define, the power of a lens is 1 diopter if its focal length is 1 meter. Note, power of a lens is positive for the converging lens and negative for the diverging lens.